Hi, chemistry students. Mr. Lopriato here, and we're just diving straight into the properties of matter. The first thing we're going to talk about the properties of matter is physical and chemical changes. All right, so these are things that we can observe. A physical change, something like an ice cube melting, we can observe that happening. We could take measurements, but that ice cube doesn't change its identity. It is water. It's water in a solid state, it's water in a liquid state as it melts, but it is still water, all right? So phase changes, solid, liquid, gas, cutting something in half, things like that would be a physical change. You're changing a physical property of the matter, but you're not changing what the matter is. And a chemical change, we can only observe by doing a chemical reaction. So if we had a fire, for example, if we had a couple of logs on fire, that is a chemical reaction. It's a combustion reaction. And so the atoms in the compounds in the wood would be changing. So they would be turning into soot and ash and things like that. So melting is physical, burning is chemical, and on the new Muppets show, they did a great segment on one of the videos. Will it burn or melt? Right, and they tested different things. They had these like flamethrowers. They saw what happened. All right. So our physical changes: crushing a can, melting an ice cube, boiling water, mixing sand with water, breaking glass, dissolving sugar in water, shredding paper, chopping wood, mixing green and red marbles, sublimation of dry ice. That's when it goes from solid to gas. In all of these examples, we're not changing the identities of the substance. Think about crushing that can. It's still an aluminum can. It's just in a different shape. The same thing with like the shredding the paper. Dissolving the sugar in water. We can boil that and the water will come out and the sugar will stay behind. All right, so we can undo physical changes by ordinary means without having to do a chemical reaction. All right. Physical properties of matter, things that we can observe, see, hear, feel, smell, touch, measure, right? Gold is shiny, that's something we see. Metal makes sounds when clanged, right? Sonorous, that's something we can hear. The feel, the way that the rubber bends on your pencil, all right? Touch, the ceramic pot is hard. Smell, acid, smell, sour, you want to waft those, right? If you were in a chemistry lab. Things we can measure, the temperature of something, the length of something, all things like that. All right, so we have all of these different versions. We get a ton of them: magnetism, shape, mass. There's a lot of different things happening here, right? Density, texture, all things that are physical properties of matter. All right, now our chemical changes. Here are the words you want to look out for: rusting. Iron rusting, that's the formation of an oxide, right? When iron rusts, it forms iron oxide. Burning, right? So burning wood, combusting would be another term. Metabolism, any of those changes in your body. Think about it. When you eat food, it looks different on the other end, all right? So it has changed. Cooking an egg, baking a cake, electroplating, rotting, vinegar and baking soda, fireworks, chemical batteries, right? So all of these are examples of chemical changes. This is where a reaction is taking place. You're getting reactants forming products. The products look different from the reactants. All right, so that's important. Think about when you have that fire pit. The wood looks different after it's burned. It's all black, it's soot, it's charred. All right, baking a cake. What happens if you bake it for too long? It burns as well. All right, cooking an egg. The egg looks completely different cooked than it did before it was cooked. All right, so our chemical properties, things like toxicity, oxidation states, heats of combustion, chemical stability, flammability, coordination number, reactivity, possible chemical bonds, enthalpy of formation. All right, the big terms that I want you to know for right now: combustion, that's going to come up a lot. We'll learn about these other terms as we go on in the year. So like oxidation states, we'll see. We're just not looking at them right now. So for chemical properties, I know the language can feel a little weird. It'll come together as the year goes on. All right, so now those are the physical and chemical properties of matter. All right, now we have these two terms, and these are important terms: intensive and extensive. All right, these are properties of matter. Intensive properties do not depend on the amount of matter, right? The boiling point of a substance is a temperature where the substance goes from a liquid to a gas. Doesn't matter if you have a lot of that substance or a little bit. If you're at that point, it's going to boil, right? The color of a substance isn't going to change whether you have a lot of it or a little bit of it, right? If you have a lot of gold, that's awesome, but the gold's not going to look any different than a little bit of gold, all right? How shiny it is, how hard. Extensive properties of matter are properties that do depend on the amount of matter present, all right? These are things that we measure, right? And as we get different amounts of matter, they can change. These are things like volume, right? How much space something's taking up, mass, the measure of the amount of stuff, right? How heavy it is, its size, its weight, its length. Those are all extensive properties. One thing I'm going to point out, I'm going to say it in this video, density is a ratio of mass to volume. Mass and volume are both extensive properties, but density in and of itself is an intensive property. Doesn't matter. The density is the same ratio whether we have a lot of matter or only a little bit of matter. All right. So I've asked you guys in the past to play the little alchemy game. I just want you to think, people were trying to break matter down into these parts. The Greek philosophers thought it was fire, air, water, and earth, which is obviously incorrect, but you know, they tried. We want to be able to break matter down. We can break matter down into individual atoms. We can keep going there, proton, neutron, electron, right, in the nucleus, and then we can get to quarks. We can just keep going deeper and deeper, right? From the quarks, we get to the hadrons and leptons, and then there's string theory holding it all together. That's not what we're worried about for right now. We just want to think, hey, can we break it down, and what do these things look like at the atomic level? All right. So we know that in our atom, hopefully we've seen this before, we got protons and neutrons in the center of the atom, that's our nucleus, and the electrons are orbiting it. We will do whole units on atomic theory, right? So we're just kind of introducing it right now. But we can use these little balls to represent individual atoms. It works really well. We can see solid, liquid, and gas, the way that atoms, or the way that matter at the atomic level looks, right? Solids are closely packed together. Liquids are close but can slide past each other, and gases typically are spread out. I would have drawn these even further spread out, truthfully. All right. Now we can have the same substance. We could think of like just oxygen. You're probably expecting oxygen to be a gas. You can get liquid oxygen if it's cold enough, and if it's really cold, you can get solid oxygen, right? So it doesn't change the fact that it's oxygen in these three pictures, but how close those molecules are dictate which state of matter it's in. So solid, liquid, or gas. These are its physical properties, but the substance that it is oxygen. All right. We can use pictures of atoms to explain this chemical reaction, right? Iron rusting, forming that iron oxide. We know that the iron pipe looks different. Well, it's because it looks different at that atomic level. So that's why we want to be thinking in this atomic level space. All right. We can see that certain elements are diatomic, which means two atoms. Something like hydrogen or oxygen, H2 or O2, those little subscripts are going to matter. We could see whole molecules, right? You probably remember sugar from biology class, C6H12O6. So we can get an idea. It's going to be this cluster of multiple atoms. These are our molecules, right? These are compounds. From water on, we're compounds. So these are pure elements. Even though there's multiple atoms in the molecule, we're going to consider them pure because it's only one type of element, hydrogen, oxygen, phosphorus, or sulfur. When we start having two or more types of elements, now we're getting compounds, water, carbon dioxide, glucose. All right, so this is another way we can make sense of, and we can split matter into two camps. We can have element versus compound, right? We're only going to have a limited number of pure elements. There's only 118 on the periodic table. The elements differ by the number of protons in their nucleus, right? And then the neutrons and the electrons will also change, but it's really the protons that give us the element's identity. So helium, for example, has 2 protons, where oxygen is going to have 8. All right. Now, a compound is when we have, again, 2 or more elements in like a cluster, they're going to be really close together. They're going to be bonded covalently or ionically, and we will learn about that. All right, but it's two or more, they're close together. This is kind of like learning letters and then putting letters together and making words. All right, so we can get a whole bunch of different ratios of different elements, and they're going to form a whole bunch of different compounds. All right, here's an example of salt, right? Common table salt, NaCl. It's going to be held together in this unique lattice structure, but it comes together. We're going to see that it's two different types of elements. So this is a compound. All right, so now matter, we can divide, and this is any matter, we can divide it. Is it a pure substance or is it a mixture? Now, we've already talked about the pure substances. It's either an element or it's a compound, but it's pure. A pure substance means that there's nothing else there. We very rarely get the chance to deal with pure substances. All right, when I go into the chemical storage room, we buy elements from different vendors. Those are pure substances. You can buy some pure substances. If you go to a hardware store, you could buy pure copper, absolutely. Aluminum foil, we could think of that, that's pure aluminum. The air we're breathing in right now, though, all right, is it pure oxygen? Absolutely not. All right, the air we're breathing in is a mixture. What type of mixtures do we have? All right, we have two definitions for mixtures, either homogeneous mixtures or heterogeneous mixtures. Now, let's think about those prefixes. Homo means the same, hetero means different. So the same type of mixture or a different type of mixture. All right, so in a homogeneous mixture, we're also going to call these solutions. Something is dissolved in something else, and it's so fully surrounded that we don't even notice those pieces. All right, so this is something like if you had a salt water solution and all the salt was dissolved by the water. In a heterogeneous mixture, we have essentially larger chunks, so it's not necessarily fully dissolved. So this would be a saltwater solution that is so salty, you can see clumps of salt on the bottom of the water, right? We would call that super saturated. You would be able to see it. So again, homogeneous, it's a solution, it's dissolved. You're not gonna notice that it's gonna appear almost to be pure, even though it's a homogeneous mixture. Heterogeneous mixture, you're gonna be able to visually spot, in most cases, the differences, all right? So another thing to think about with a heterogeneous mixture, it's very unevenly distributed particles, all right? So a great example would be like the ingredients on a pizza, all right? If you're at home and you know, you have a supreme pizza, do you want the slice that has more pepperonis and less olives on it, or maybe a slice that has you know, more onions, things like that? You can look at that pizza and you're going to be able to spot like which slice you want based on what you like, because not every slice of pizza is going to be exactly even the exact same amount of every single ingredient. A salad would be another example. If I had a bowl of salad and I scooped out 10 plates, is every plate going to look identical? Absolutely not, right? Someone might get 3 tomatoes, whereas someone's only going to have 2. You know, we're going to see those differences. Think about like a bowl of M&Ms. My favorite type of heterogeneous mixture is like if I go to Chipotle. I'm going to Chipotle, I get up to the counter, they ask me what I want, and I say, 1 heterogeneous mixture, please, right? And they're going to put the rice and the peppers and onions and the meat, and they're going to put it all in a bowl, and it's going to be really unevenly distributed. All right, so again, like a fruit salad, a bowl of Skittles. Think about dirt, right? You go outside, you pick up a scoop of dirt. You might have a rock in it, you might have a worm. Who knows? But it's not necessarily going to have an even composition. All right, gold in your poop. This is a pretty interesting article. Scientists found in a site, in a waste treatment site near an old gold refinery, they were actually getting traces of gold. And if someone wants to, a company can come along and sift through all that poop, and they will be able to collect roughly $1 million worth of gold. But do you want to do that job? Maybe, maybe not. Probably not. I don't want to do it. I'm just going to teach you guys instead. All right. Now, a homogeneous mixture, it's going to have a uniform appearance. It's going to look all the same. And we have a couple of examples here. Think of a lot of like drinks, a Kool-Aid drink, iced tea, things like that, any of those powders that you add to the water, you stir it, it dissolves, it has that uniform appearance. It's gonna appear as just that liquid. The exception there is when you add too much of the powder. I had a friend in high school who, whenever we'd go over his house, he would make iced tea, and he always joked. He called it diabetes in a cup. He used twice as much iced tea mix than it called for in half the volume of water. So it was like super sweet, and the bottom of your cup would be literally like this like slush of sugar. It didn't fully dissolve, so that was a heterogeneous mixture. But if we used the proper ratios, it would have properly dissolved. It would have been a homogeneous mixture. And spoiler alert with him, he called it diabetes in a cup, and he actually has diabetes now. So please don't be making terrible decisions right now at this point in your life. They will carry over later. All right. Perfumes, colognes, all right, they're liquids. When you spray them, they aerosolize, all right, but these are homogeneous mixtures as well. Lots of different chemicals in the perfumes. I think this is one of the coolest things. It's a lab we can do later in the year, hopefully, where we can actually make different compounds that'll smell like different fruits. All right, but all different perfumes, there's a lot of chemistry going on. I have this picture of a trumpet, because the trumpet is made out of brass. Brass is an alloy of two metals, copper and zinc, and it's one metal that is actually dissolved in the other metal. All right, and it is a homogeneous mixture. All right, so it appears like it's a pure substance, but brass is an element or a compound. It's actually a mixture. Again, we call it an alloy. So they're not bonded to each other, they're just near each other in that solid structure. All right, and the zinc is dissolved amongst the copper atoms, which is pretty interesting. So we got a couple of different types of alloys. Now, something that's important about a mixture: if the mixture will settle out over time, then it really was never homogeneous. It was actually a heterogeneous mixture. A good example of that, if I asked you if coffee was a heterogeneous or a homogeneous mixture, it would depend. How do you drink your coffee? I drink black cold brew. That would be a homogeneous mixture. It's all one thing. It doesn't settle out. Maybe you add milk and sugar, and if it clumps at all, anything like that, like if you're adding like those cool foams at Starbucks, if you're getting like a frappuccino and they're doing that caramel drizzle and they're putting sprinkles on top and whatnot, that's definitely going to be a heterogeneous mixture. But again, if you can either visually see something or if it settles out over time, heterogeneous mixture. If I asked you, is your blood, what type of mixture is that? A lot of people think homogeneous because it looks like it has a uniform composition, but when we zoom in on blood, we actually see it's got red blood cells and all these other different things going on, platelets and whatnot, white blood cells. So blood is actually a heterogeneous mixture. It will settle out over time if we let it. All right, so again, mixture, hetero or homogeneous, unevenly distributed or evenly distributed. So those are the big pieces we're looking in this very first chapter that explain how we can classify and begin to organize matter.